Thank you for joining while I discuss our investigation of unmanned aerial vehicle gesture perceptibility and the impact of viewpoint variance. My name is Paul Fletcher, and I am presenting on behalf of the Nimbus Lab at the University of Nebraska-Lincoln. Unmanned aerial vehicles are being used in public domains and hazardous environments, such as search and rescue or prescribed fire ignition, where effective communication strategies are critical. Gestural communication has been studied by researchers and has shown promise as a lightweight and functional communicative mechanism, which may prove especially useful in the domain of unmanned aerial flight. For example, UAV durations are constrained by the relationship between hardware and battery power, making software-oriented communication strategies such as gesture especially useful and easy to implement. Gestures may also be useful in contexts where environmental noise inhibits other communication devices, such as light and sound, or if those devices fail. However, researchers have noted that due to the visual nature of gestural communication, perception of gestural motions can often become obscured from varying observer viewpoint perspectives. The figure on the right demonstrates how different viewpoint perspectives can obscure the perceived shape of a UAV gesture's motion. In viewpoint A, all of the motion along the y-axis is visible, showing the full shape of the gesture's motion. However, in viewpoint B, some of the motion in the y-axis is occluded, distorting the perceived shape of motion. In viewpoint C, all of the motion in the y-axis is occluded, making the shape of motion resemble a vertical line instead of the intended figure 8 shape. We explore how observers perceive two-dimensional gesture motion from varying viewpoints, specifically as the viewpoint rotates along the z-axis, either obscuring or revealing more motion along the y-axis. To do this, we conducted 3 online surveys using Qualtrics. In each survey, we showed participants a series of point animations and asked them to classify the shape of the motion among a series of choices. We've recruited a convenience group of 81 participants via Amazon's Mechanical Turk. All participants were required to have a master rating, demonstrating a record of high-quality responses. In each survey, we included multiple attention tasks to ensure the participants fully viewed each animation before responding. In this work, we state and examine 4 hypotheses. First, that participant response accuracy will improve as gesture viewpoint rotates away from the most occluded angle. Second, a historical model of viewpoint rotation will yield higher response accuracy than random viewpoint rotation change. Third, at some viewpoint perspective, gestures will be perceivable with an accuracy probability of 0.9 or 90%. And fourth, the proportion of total motion in the z-axis for a planar gesture will correlate positively to perceptibility. In our first survey, our goal was to assess how much a participant needed to rotate the viewpoint to be able to accurately identify the shape of a gesture's motion. Each gesture was first shown to participants from the viewpoint where all of the motion in the y-axis is occluded. The figure on the right demonstrates the gesture's motion a participant would see, while we include the figure on the left here to clearly display the motion's shape. Participants were then given 2 options: to rotate the angle of the viewpoint or to choose the shape of the gesture's motion. If participants chose to rotate the viewpoint, they would then be shown an animation of the same motion from a viewpoint rotated 5 degrees about the z-axis. As participants continued to rotate the viewpoint, the shape of the gesture's motion became clearer. Participants were able to rotate the viewpoint 90 degrees in total, displaying the gesture in a fully non-occluded state. Survey 2 was very similar to Survey 1. However, instead of beginning the survey at the most occluded viewpoint, we began at the viewpoint 20 degrees away from the most occluded view and asked participants to rotate the viewpoint and classify the motion shape when confident. The purpose of Survey 2 was to understand if participants needed to see some degree of prior viewpoint rotation in order to understand the shape of motion by building a historical model of the motion. In both Survey 1 and Survey 2, participants were shown 6 gestures, with 3 gestures randomly repeating once, totaling 9 classification tasks. Gestures were presented in a random order. In Survey 3, we have removed the participants' ability to rotate the viewpoint perspective, and gestures were shown to participants in random order. Based on the results of Survey 1 and 2, we chose to limit the range of viewpoints from 0 to 50 degrees away from the most occluded viewpoint. Participants were asked to classify 6 different gesture shapes at 11 different viewpoints and to rate their confidence in their classification. In each survey, we tested 6 different gesture shapes. The figure on the right demonstrates the full shape of each of the gestures in the set. We identified our gesture test set based on prior work in UAV gestural communication, which demonstrated some efficacy in communicating meaning to untrained observers. We conducted a logistic regression on the results of each of our surveys to characterize the relationship between degree of viewpoint rotation and response accuracy. The analysis yielded a predictive curve indicating the probability of accuracy at particular viewpoints. The figure on the right demonstrates that as the viewpoint angle increases, response accuracy increases in the case of each survey. The results of our logistic regression analysis from Survey 1 and Survey 3 support this relationship, both yielding positive regression coefficients and p-values less than 0.01, thus providing support for Hypothesis 1. While the logistic regression from Survey 2 yielded a positive regression coefficient, the results were not statistically significant with a p-value of 0.28. We believe this may be due to a high distribution of responses at the initial viewpoint angle in Survey 2. We also chose to compare the accuracy values from Survey 1 with those from Survey 2 and 3 at 20 degrees of rotation to determine if a historical model of the gesture's motion improved response accuracy. This figure represents the response distribution and proportion of accurate responses by viewpoint for each of the surveys. In Survey 1, accuracy is well over 90% at 20 degrees of viewpoint rotation. However, in Survey 2 and Survey 3, accuracy is much lower, just over 80% in each case. To evaluate these relationships, we conducted two one-tailed hypothesis tests comparing the proportion of accurate responses from Survey 1 at 20 degrees against those from Survey 2 and Survey 3. However, the results were not statistically significant in either case. We believe this is also due to the low number of participant responses at 20 degrees of rotation from Survey 1. Overall, these results do not provide support for Hypothesis 2. We chose to characterize an accuracy threshold where participants are able to classify a gesture's motion with at least 90% accuracy. Predicted 90% accuracy values range from viewpoints at 20 degrees in Survey 1 to 30 degrees in Survey 3, with the results of Survey 2 predicted 90% accuracy at 25 degrees of rotation. These results suggest that a 90% accuracy threshold exists between 20 and 30 degrees of rotation. However, these models include the circle gesture, which proved to be a statistical outlier, demonstrating poor response accuracy across most viewpoint perspectives. This may be due to a lack of identifiable motion characteristics in the z-axis, which will be discussed further in the next section. To characterize a 90% accuracy viewpoint threshold, we conducted a 1 proportion z-test on response accuracy values from Survey 3 for all gestures except the circle. The results suggest that, beginning at 20 degrees of viewpoint rotation, observers will be able to classify the shape of a gesture with at least 90% accuracy. These results are statistically significant, with a p-value of less than 0.01, providing support for Hypothesis 3. In addition to examining response accuracy with respect to viewpoint, we were interested in characterizing the overall perceptibility of individual gestures. To do this, we created a perceptibility scoring metric that accounted for response accuracy, participant confidence, and the number of times a participant chose to view an animation for any particular task as a measure of classification difficulty. These scores were weighted based on the distance of the viewpoint from the most occluded angle. For example, higher perceptibility scores were earned for gestures where a large number of participants were able to accurately and confidently assess the shape of a gesture's motion at an early viewpoint while viewing the animation a limited number of times. We calculated total perceptibility scores for each gesture tested in our study, with the results given in the figure on the right. The circle gesture demonstrated the lowest overall perceptibility, while the undulate and swoop gestures demonstrated the highest perceptibility scores. To understand why this may have been the case, we calculated the total proportion of motion in the y and z axes respectively for each gesture. It is important to note that at the most occluded angle, only motion in the z-axis is directly visible for each gesture. Given this, it may be that higher proportion of motion in the z-axis could create more identifiable gesture features earlier on when rotated. The figure also demonstrates the total proportion of motion in the z-axis for each gesture. We conducted a Pearson correlation analysis to examine the relationship between perceptibility and z-axis motion, demonstrating a strong positive correlation with an R-value of 0.77 and a p-value less than 0.1, providing some support for hypothesis 4. The primary finding in this work is that across 5 of the gestures tested, 90% gesture classification accuracy is achievable at 20 degrees of rotation away from the most occluded viewpoint. One gesture, a circular motion, represented an outlier as observers were unable to achieve 90% accuracy before 40 degrees of viewpoint rotation, which may be due to a lack of identifiable motion characteristics in either axis. Of the gestures tested, we identified a strong positive correlation between overall perceptibility, defined by a perceptibility scoring system, and the proportion of total motion in the z-axis, indicating that more motion correlated to higher perceptibility. While our work has demonstrated that participants are able to perceive shape from motion in our animations, the results have yet to be confirmed in field settings with real UAVs. In addition, the 90% accuracy threshold may be limited to the set of gestures tested in this work. Future work will examine whether the quantified viewpoint threshold will generalize to new gestures and also compare these results to trials in field settings. Thank you very much.